So in this lecture, what I'd like to do is to start talking about one more application of integration before we start getting into problems about how do we actually find the antiderivatives of things that are maybe more complicated than what we can handle just by recognizing derivatives or using substitution. So that's what we'll get to next week. But for today, I want to talk about one more application of integration. And this one is in some ways I kind of think maybe in some ways it's a little more straightforward than the sorts of situations that we have been looking at before. So there's a couple of different ways of approaching this. And the topic that we're going to look at here is what is the average of a function f on an interval from a to b. What would this mean? Well, for one thing, it would mean that I need a better pen, because that's not writing so well. But what would this mean to have an average? Well, if the function happened to be piecewise constant, in other words, if the function were constant on various parts of the interval, so let's say here's A, here's B, and if my function were effectively constant on different pieces of the interval, then the sensible thing to do would be to say that the average value, if a function is literally constant, then the average is just whatever it is. If the function is constant on different pieces, then the sensible thing to do would be to say that the average is given by these different values that it takes, weighted by the length of the interval over which it has that value. In other words, we would say that the average is going to be, let's say this is x1, x2, and so on. Well, then the average should be obtained by taking f of x1 star times x1 minus a plus f of x2 star times x2 minus x1. And we would keep on going like this. Maybe there's, I only drew 3 here, but you might have more than this. I just didn't feel like making my drawing even more cluttered. But then we would want to divide this by the total difference between b minus a, because otherwise we would end up multiplying. If this were just literally a constant, we'd end up with the function times the width of the interval, and we would actually, for a constant, just want it to be the value of the function. So we need this 1 over b minus a in order to make that work. And then what we can do is we can say, well, actually, we can make this kind of sum work as an approximation even if f is not piecewise constant. What do I mean by piecewise constant, by the way? I mean it's a piecewise function, and on each interval, it's just one specific value. So it's a piecewise function where every single expression is just a constant. These are also sometimes called step functions because they end up looking like a bunch of steps, although sometimes they go up and down in crazy sorts of ways, but each piece is just a constant. Now, this works as an approximation even if my function is not piecewise continuous. So even if I have something like that instead, I can still use this method as an approximation. And in the limit, as the approximation gets better and better, well, this just turns into an integral. And so what we end up with is 1 over b minus a times the integral from a up to b of our function. And we define this to be, this is the average of f on the interval from a to b, assuming it exists. Now, I want to say that there is another reason why we would define this as the function, and it's closely related to this approximation idea, but I think it does sort of give us a little bit of a more intuitive understanding of why this is what we get. So let us take a look at another sort of way of thinking about this. Well, one of the ways of kind of thinking about what is an average, if I have a list of things, the average of a list of things, like usually we write that with a variable with a bar over it. This is usually written as everything in the list added up divided by the number of things in the list. But one of the properties that this has, therefore, is that the number of things in the list times the average is the sum of all the stuff in the list. In other words, you add up all the stuff in the list, it's just the number of things times the average. Well, this value here, this average, has a similar sort of property, except the property that this has is that the average of f times the length of the interval is 1 over b minus a times the integral from a to b, f of x dx, times b minus a. The b minus a's cancel, and this leaves me with just the integral from a to b of f of x dx. So this kind of property is really another reason to think of this as the average. If you take the average times the width of the interval, you get the integral. And this makes a lot of sense. For instance, let's suppose that my function is, instead of being f of x, what if I had v of t? A velocity function given as a function of time, right? This is sort of a physicsy application here, but it's one that comes up a lot, and it's one that's kind of reasonably simple to visualize, because going on a journey at a different speed is something that most people always think of. Well, the total displacement from t equals a to b is given by the integral from a up to b, v of t dt. In other words, the total that I move is given by integrating my velocity function. But what should be the average velocity? Well, the average velocity should be the velocity that I would need to travel if I traveled at a constant velocity in order to, over this time interval, have the same displacement. So the average velocity, v average, we would expect this to have the property that b minus a times v average should be equal to the total displacement. Like, that is the sensible thing to say. This is what it means to be the average velocity. However, the average velocity is just this integral time. Like, in order to make that work, the total displacement is this integral, so the average has to be this integral divided by b minus a, so that it cancels and leaves me with just the total displacement. So we have to have the average velocity be 1 over b minus a times the integral from a to b, v of t dt. So this is sort of another way of reasoning why we define this as the average of the function. And of course, these are closely interrelated, because if you think about a velocity which is piecewise constant, well, then what is this integral? It's literally just one of those approximations we wrote down. And then in that case, the approximation is no longer an approximation, it's an exact value. But for an arbitrary velocity, then those are approximations, and in the limit, as the approximations get better, this is what we end up with. One way or the other, this gives us a way to think about the average of something. So, let's think about the following problem. Let's suppose that we want to just find the average of f of x is equal to, let's say, x squared plus 3 on minus 1 up to 3. Well, this is actually pretty straightforward as long as I remember the definitions. This is, I mean, there's a lot of things in math that are like this, right? You have to remember what something means, but if you remember what it means, then like actually doing it can sometimes be kind of not too difficult. In this case, it's straightforward because what I write down, what I'm going to have is 1 over 3 minus negative 1 times the integral from minus 1 up to 3 of x squared plus 3 dx. And so what I mean by this is straightforward is there's no real tricky things about this integral. It's just a polynomial that's being integrated, so we don't have to break out any major tricks to do this. This is then going to become 1 over 4 times, we're going to have x cubed over 3 plus 3x evaluated from negative 1 up to positive 3. Well, that becomes 1/4 times 3 cubed over 3 is 9 plus 3 times 3, that's another 9. And then I'm going to be subtracting negative 1 cubed is negative 1, so negative 1/3. And then we're going to have minus 3. So this becomes 1 over 4. So this is going to be 18 plus 3 1/3. That's 21 1/3, or 64 thirds. And 64 divided by 4 is going to be 16. So we end up with 16 over 3. And there we go. That's our answer. Now, there's kind of a nice way of visualizing what's going on with these averages that maybe we can sort of illustrate here. Let me erase the actual work here. If you need to go back and see what we said, then please feel free to do that. But so this is the picture that we have of what's going on here. X squared plus 3. It crosses the y-axis at 3. We're going over here between minus 1 and 3. And so what we get is this piece of a parabola looking like this. And there's some sort of area in this region. Well, the area of this region is the same as the area of a box at a height of y equals 16 over 3. So this area down here and this area that is in this box, they are the same. So that's kind of another way of thinking about the averages. The average is, we're asking, what height would a function have to be in order to say this is a constant function whose integral is the same on this particular interval as whatever function we are dealing with here. Think back to what I said about the average velocity, right? The average velocity came from saying, well, we want to know what velocity would we have to go if we wanted to do a constant velocity to end up with the same total displacement. So another way of thinking about the average of a function is that we want to say that the average of a function, f average, should have the property that the integral from a up to b of f average is equal to the integral from a up to b of f of x dx. However, this on the left, this is the integral of a constant. And for a constant, this is just the width of the interval times f average. And on the right-hand side, we have the integral from a to b, f of x dx. Well, that means we must have that the f average is equal to 1 over b minus a times the integral from a to b of f of x dx. So this is kind of the same sort of argument as I made with the velocity functions, except this time, instead of thinking about a velocity function, I wanted to just think about an arbitrary, abstract sort of function. I am still unhappy with the performance of this marker. Perhaps this marker will do a little better. So there we go. There's some stuff about averages. Now, of course, in practice, we can talk about certain questions with averages that are maybe a little bit trickier. Like, let's say that a ball is thrown on a given trajectory, and the height of the ball as a function of time is going to be equal to 2 plus 20t minus 10t squared. And we want to know what is the average height from being thrown to landing at a height of 0. So we assume here that it is being thrown at t equals 0. T equals 0 is the start of this process. We want to know the average height for when it lands. So we got to figure out, when does it land? Well, in order to do that, we're going to have to take negative 10t squared plus 20t plus 2 and set this equal to 0. Now, when we do this, this is the same as minus 5t squared plus 10t plus 1 being equal to 0. And this doesn't factor nicely, unfortunately, because I don't have two numbers that add to 10 and multiply to negative 5. So we're just going to have to use the quadratic formula here. Or you could use completing the square. But most people, I think, prefer to use the quadratic formula. So I'm going to have negative 10 plus or minus square root of 10 squared minus 4 times minus 5 times 1 divided by 2 times minus 5. This is going to become 1 plus or minus the square root of 120 divided by 10. This would normally be a negative 10, but since we have a plus or minus here, I can absorb that negative into the plus or minus. It really just turns this into a minus or plus. And what can we say about the square root of 120? Well, that is going to be the square root of 10 times the square root of 12. So this is actually 1 plus or minus, let's see. Square 12 is 2 times 2 times 3. So this is 2 square root 30 over 10, which is 1 plus or minus the square root of 30 divided by 5. Okay, now we need to figure out which one of these is the landing. Well, here's the thing. The square root of 30 is a little bit bigger than 5. So 1 minus square root 30 over 5 is a negative number. In fact, if we look at this, what we see is that we get this upside down parabola that looks like this. These are the two intersections we're talking about. But the throw happens at t equals 0. And therefore, I don't care about anything that happens on the left-hand side here. I can just throw that away. This equation, or this formula, doesn't even describe what's going on at those times. It's just nothing. Well, it's not nothing. It's not described by this because I didn't throw the ball yet. So the throw only applies when t is positive. So I want to take the positive option. So it lands it reaches a height of h equals 0 when t is equal to 1 plus square root 30 divided by 5. Now, make sure that you kind of see what's going on here with this example so far, because I'm going to have to get rid of some of this stuff in order to work out the next bit. So what we're really asking is for the average from t equals 0 to t equals 1 plus square root 30 over 5. So what do we have? Well, we're going to have 1 over 1 plus square root 30 divided by 5 times the integral from 0 up to 1 plus square root 30 divided by 5 of this h function, negative 10t squared plus 20t plus 2 dt. And there we go. That's pretty much all that we can really say about this. Well, we can now figure out what this is going to be. It's going to be whatever this comes out to be. How much can we simplify this? So we can say this is the same as 5 plus square root 30 over 5. And so this is the same as 5 over 5 plus square root 30. And then this is going to be times negative 10 over 3t cubed plus 10t squared plus 2t, evaluated from 0 up to 5 over 5 plus square root 30. And now it's just a matter of evaluating this. Now, I'm going to be honest, you probably want to just evaluate this by plugging in a decimal approximation onto a calculator or something. I wouldn't normally expect you to go through and plug in such a nasty number, because like when I cube this is going to turn into a true mess. We could also rationalize these things, but frankly, usually when you're doing a problem like this, now normally I am all in favor of exact answers. I say, don't put decimal approximations. But when you're dealing with something like this, a decimal approximation is usually fine. If you really wanted to work out what this comes out to be as an exact value, there are computer programs that can do that for you so you don't have to do it by hand. Now, we can do it by hand. I'm not saying it's impossible to do by hand. It's not hard to do by hand in the sense that it requires anything tricky. It's hard in the sense that it's long and annoying because, well, we have to do things like cube this crazy fraction that involves square roots in it. Even if I rationalize this thing by multiplying on top and bottom by 5 minus square root 30, I still have to cube the resulting fraction, which involves square roots. So that would be some work. See, the thing is, again, I can do this by hand. It's just I would end up filling the entire wall of my office with these calculations. And if you're doing something like this, you probably just need to know approximately the average height. And so you may as well just do it using a decimal approximation. So the good thing is that averages for functions are actually not super difficult, really, as long as you know how to do the resulting integrals. Certainly, I think compared to dealing with those awful pumping problems that we talked about previously, I think this is a lot easier. And by the way, I'm going to post some other people talking about pumping problems because I want to have you guys have the opportunity to hear about those pumping problems from multiple people, not just me. Their method of explanation might make a little more sense to you than my method of explanation for some of the problems, or maybe my explanation works better than theirs. But hearing different perspectives is really important. And I think one of the nice things about having this course running in this format is that it's very easy for me to incorporate information that other people have recorded or whatever into our learning here. So it makes it possible for you to kind of learn not just from me, but from other people out there as well. So that's kind of why I didn't do as much lecturing on them. I wanted you to actually see these examples done by different people and hopefully answer your questions. Anyway, returning to the matter at hand. As you can see, these averages questions are somewhat easier to set up usually than those pumping in and out of a container type problems with involving work. Now, there is a bit of a related result that we can get from averages, and it's really cool, and it's interesting how easy it is in some sense. And because of that, I want to show you this trick, even though it's maybe not one that is necessarily new to you, but I want to show you the intermediate value theorem, which we usually abbreviate as IVT, for integrals. The intermediate value theorem for integrals says the following. If f of t is continuous on the interval from a up to x, then there is a c in the interval from a to x with f evaluated at c being equal to the average value on the interval from a up to x. Now, intuitively, this is almost obvious. If I have a function from a up to x, and I look at the integral of this thing, and I want to have a constant function whose integral gives me the same value over this interval, well, obviously, the height of that function is going to have to sit somewhere in between the maximum and the minimum of these functions. So to say that this rectangle has the same area as the region under this curve, yeah, the top of the rectangle is going to have to cut through the curve, because it can't be bigger than the maximum and it can't be smaller than the minimum. So geometrically, this is almost immediate. And that is literally how we're going to prove this thing. We're going to say, well, I want a number that sits in between these things, and we're going to show that that average number is going to have to be in between the maximum and the minimum, and then we will simply apply the, not the intermediate value theorem. Why did I say intermediate value theorem? I know why I said intermediate value theorem. Mean value theorem. I said intermediate because that's what we're going to use. So that's why I threw myself there. We then apply the intermediate value theorem to say, and because it's between the maximum and the minimum, and f is continuous, it has to hit that value. So here is how we can prove this. What we can say is this. Let's say that m is the maximum of f on the interval from a up to x, and little m is the minimum of f on a up to x. Then what we can say is that the minimum times x minus a is less than or equal to the integral from a up to b, a up to x of f of t dt, which is less than or equal to the maximum times x minus a. But then what we can say is that the minimum is less than or equal to 1 over x minus a, integral from a up to x, f of t dt, less than or equal to the maximum. But this is literally just f average. So the average value has to sit in between the minimum and the maximum. By the intermediate value theorem, there is a c in a up to x with f of c equal to f average. And we are done. We just don't have a lot of space for our little end in the proof box. Look at how easy this proof is. Compare this to the proof of the mean value theorem for derivatives. The proof of the mean value theorem for derivatives is actually kind of obnoxious. It's not awful, it's not like terrible, but it's much more complicated than this. Now normally when we deal with derivatives, what we do with our derivatives is easier than with integrals, but this is an exception. This is one of those cases where it's actually easier to prove the result for integrals than it is to prove it for derivatives. Now, the thing that you might be wondering is, what's the connection? Because this is the mean value theorem for integrals. How is this connected to the mean value theorem for derivatives? Well, the answer is the two are equivalent and they are related by the fundamental theorem of calculus. Because notice that now that I have this result, remember that the derivative of the integral from a up to x of f of t dt is equal to f of x. And what we just said is that there is some point where this derivative has to equal the average. Well, what you get from this is that there has to be some point in the interval where the derivative of this function is actually equal to the average rate of change from one end to the other, because the average rate of change of this function here, which I'm going to call capital F of x, well, that's really just the average of the derivative of capital F. But what this is saying is that there is a point where f prime of c is equal, because f prime of c, this is really f of c, and this point c, where f prime of c is equal to capital F of b, or of x, minus capital F of a. And that is really the mean value theorem written for derivatives. We've just written it out for capital F instead of little f like we normally do. If you look in your book, problem 25 in the homework, and I want to encourage you to look at this, problem 25 explains how you go from the mean value theorem for derivatives to the mean value theorem for integrals. So I proved the mean value theorem for integrals without using the mean value theorem for derivatives. But if you already know the mean value theorem for derivatives, you can get the mean value theorem for integrals with it as well. However, if I were teaching people sort of from the ground up, I would say it is actually easier to prove the mean value theorem for integrals and use that to prove the mean value theorem for derivatives, rather than trying to prove the mean value theorem for derivatives first and then get the one for integrals. You can do it in either order because these are logically equivalent results. But the mean value theorem for integrals is so nice and simple to prove. The mean value theorem for derivatives is, again, it's not terrible. I'm not saying it's the worst proof I've ever seen in my life, but it's definitely longer. At least if I'm remembering correctly, it's definitely longer. And so I think that approaching this for integrals is easier. There are some other things in mathematics also where the results of certain things for integrals are a bit easier to see or to prove than for derivatives. And so normally we think about differentiation, taking derivatives, as the easier side of things versus integration, antiderivatives, and that is true. Or rather, anti-differentiation is harder than differentiation. But integration, that can sometimes be relatively easy to work with and nice to work with compared to differentiation, because sometimes you get something where it just all comes together like this. So there we go. We have the mean value theorem for integrals. And of course, you can answer questions about this like, find an actual point that has this value. So for instance, going back to that example at the beginning, we could say use the mean value theorem to show that x squared plus 3 has a point in -1 to 3. Let me name this f of x. Has a point C with f of C equal to 16 over, crap, what did this come out to be? Now I don't remember off the top of my head. 16 over 3? Let's just work this out again really quickly. So the average value here, the integral from -1 up to 3, x squared plus 3 dx, this becomes x cubed over 3 plus 3x, and we're evaluating from -1 up to 3. So we ended up with 9 plus 9 minus -1/3 minus 3. And this came out to be, 64 over 3. And then we have to multiply through here by 1/4. So 16 over 3. Just making sure I'm not going crazy in my memory here and we're actually doing the right thing. So, sorry, that was nothing new. That was me verifying that I didn't do something silly. And then we could ask to find an example of such a C. Now, remember, the mean values theorem says there's at least one point, but there could be more than one. Well, what we know here is that the average value is equal to 16 over 3. We found that in our first example here. And x squared plus 3 is continuous because it is a polynomial. We know polynomials are always continuous on this interval from -1 to 3. So by the mean value theorem, there is a C in -1 to 3 with f of C equals 16 over 3. Then how do we find such a C? Well, the answer is we just set up the equation. We set x squared plus 3 equals 16 over 3. That's going to give me x, or rather, I guess I should say C squared plus 3. So then I get C squared is equal to, let's see, 16 minus 9 is 7, so 7/3. That means C is equal to plus or minus the square root of 7/3. Now we need to be careful because we want to make sure that C is actually in this interval. The negative square root 7 over 3, this is not in this interval because square root 7/3 is bigger than 1, so negative square root 7/3 is to the left of -1 and is not admissible. But positive square root 7/3, that's fine. That does sit in this interval. So my answer here is that the positive square root 7/3 is the only place where this happens. In this case, there is only one such value C, but 1 is all we get from the mean value theorem. There might be more, could be more, nothing to say there has to be just 1, but there has to be at least 1, and in this case, that's all you get. Okay, so hopefully seeing that has kind of shown you how even though integrals are rather complicated things, usually, sometimes they can be used in really powerful ways to give us powerful results that are fairly straightforward. I mean, imagine if we introduced integration back before you had done the mean value theorem in Calculus 1. We could have so easily proved the mean value theorem and then used that for derivatives. Well, that would have been in a lot of ways an easier way to go about it. The reason we don't do it that way is just because normally, essentially because in order to do it, we would need to define integration, and people usually want to save that until later. But yeah, it can actually make your job a lot easier, and it can give you an easier way to find certain results. All right, so I'm going to end there, and what we're going to try to start next is some new techniques for integration.